Hey everyone, we have Martin joining us today from TU Wien. Martin is a member of the Vampire team, which is a another equational theorem prover that uses a different suite of techniques that I have been excited to learn about for some time. So, Martin, I'm very excited to have you here, and please take it away whenever you're ready.
Okay. Yeah, thanks for the invitation. And yeah, I hope I can bring something to this community. So the talk is about equality reasoning in Vampire. You can hear me well, right? Because I can hear some echo from the room, but...
Yes, it's great.
Okay, then I just go ahead. Yes. Oops. Yes. So here's the outline of the talk. And yeah, I want to start with some kind of lightweight introduction into superposition reasoning. And I hope that some of you at least don't know superposition that much, such that I can show something new to you. So it will be more about the intuition behind superposition, and then I will give a bit of more formal definition of superposition and saturation, and then I will talk about redundancy, which is a very important part of saturation and superposition-based theorem proving. And then I will talk about a particular redundancy elimination technique called demodulation. And yeah, so initially I wanted to talk about code trees and term ordering diagrams, which are two initial parts of making demodulation very efficient, but I realized that I won't have enough time to cover code trees, so I would only go for the more recent work, which is term ordering diagrams. So sorry for the false advertisement. Maybe next time I can give you also a talk about code trees. So let's start with a kind of problem statement, what we want to solve. So we are looking at equations, possibly quantified, and we want to check whether two terms S and T are equal modulo these equations. And so in other words, we want to decide the validity of this formula, and we also call this UEQ formula in our community. And this, I mean, it's not in first order logic, but it's only a small fragment of it, but it is a very exciting fragment. And there is also the CASC competition where there is a unit equality track, and this is usually the most exciting part because these problems are very hard. And so this problem is already undecidable. But now let's focus on an even smaller fragments, on just ground things, so no quantifiers involved. And I will display terms with these dots. So we have S and T, and we want to somehow connect the two with equations. So the idea zero, which is, well, not a really bad idea, but we don't really use it in practice, is to just enumerate all terms that are equal to one of the terms until we find the other term, modulo this equational system. So what we do is start from one of the terms, let's say S, and just start enumerating terms that are in the vicinity of S, so to say, with respect to the equational theory. And we do this until we find T. But this approach has many problems. Well, first of all, if you don't want to miss T while enumerating the terms, you want to do some kind of breadth first search. But this also means that you will be enumerating lots and lots of terms. So if you're also working with equality, so I guess you know the struggle of the search space explosion that comes with equality. And otherwise, if you use some kind of heuristics to reach quickly T, well, you can use such things, but the problem is there are no real heuristics, or there is no real guidance to guide you towards T. Because, yeah, just because two terms are equal or because you have reached some term, it does not mean that you have gotten any closer to T. Or it's really hard to define such heuristics. So instead, we will use this second idea and we introduce some kind of ordering over terms with the following properties. We want it to be well-funded, so when we go downwards, it should terminate. We want it to be monotonic, so if two terms are ordered in a certain way, here L and R, then if we place these terms as subterms into some bigger terms, then those terms should be ordered in the same way. This is a very natural property because when we are replacing things with ordered equalities, then we want these things to be also ordered in the same way. And we also want this ordering to be total over ground terms. This is also a very natural property, I think. So we, at least on the ground level, we want to be able to compare everything fully. Okay, so this gives us a kind of direction, and here on this diagram, this direction is upwards. So S is smaller than T. And now let's imagine that there is some path between these two terms. And I will denote this path, this unknown path with red dashed lines, so that this is not yet enumerated or explored. But let's assume that there is something like this. And the second idea that we want to do is we want to, instead of trying to reach from one term the other, we want to reach from both terms, kind of the smallest term on this path with respect to the ordering, while also never going upwards. And this is very important because so as I said, the ordering is well-funded, but if we go upwards, then we lose this property and we may never terminate. I'm not saying that this shouldn't be ever done. Like there are actually techniques which go upwards in the ordering, but usually going upwards is not a really good idea, and this is not done in superposition reasoning. So let's see how this works. So from T, for example, we can go upwards once, but then this is where we get, basically. So from S and from also this term here, we have to go upwards, and we're kind of stuck. So let's look at how this, for example, this rewrite, and so from T we reach this smaller term, and from there we have to go upwards again and then downwards. And if we look at how it looks like, we have some term T prime, which contains some term R1, and we use an equation L1 equals R1 to go up and get this term T prime L1. And there is also a second rewrite after this, and there are three cases. Either L2 is a subterm of L1, or L1 is a subterm of L2, or none of these, or neither of these, and the two terms are in parallel positions. So let's say we have the first case. So our rewrite looks like this. So we have L1 and it contains a subterm L2. And with the second rewrite, we rewrite this subterm and we get T prime L1 R2. And now consider this inference, which is actually an instance of a superposition inference, or a superposition inference rule instance, where we actually take the two equations, and since we know that L2 is a subterm of L1, we can just rewrite this with the other equation and get a new equation, which is L1 R2 equals R1. And if we do this now, actually we get a new path, a shortcut from T prime R1 to T prime L1 R2. And this is good, this is what we wanted. So by doing this inference instead we get something that is, this is actually, it will be a smaller equation, in some sense of smaller, that I will talk about a bit later. And we can now connect to this term, and this is what we do. And so from T we have reached the term as desired, but from S we haven't yet. So on the other side we can do a similar kind of analysis. And we also have the three cases here, that L3 is a subterm of F4, or the other way around, or they are in parallel positions. Now let's say, for the sake of this example, because actually the second case is symmetric to the first case, so now we only have to look at when they are parallel. So let's assume that they are in parallel positions. And this means that, so we go up and rewrite R3 into L3 and then L4 into R4. But actually, because they are in parallel positions and because the ordering is monotonic, what we can do also is first So we can just swap the order of these inferences and first rewrite with L4 equals R4 and then rewrite the other term as needed. So in this case, when the terms are in parallel position, we don't have to perform any additional inference. We just know that we can swap the two inferences and get first a smaller term. And this is what we do. And for the rest of these paths, we can do similar tricks. So we can look at these two equations and let's say they give some superposition. The result of this superposition gives us a shortcut here, and we do this again and reach this, let's say, common normal form for S and T, and this establishes that the two terms are actually equal. Now, of course, this example was based on the assumption that we know this path. This is, of course, not true in practice because otherwise the task would be trivial. So with this idea 1 and 2, we only need one extra inference rule, which is superposition plus, well, actually equality resolution, if we consider not just going from S to T, but if we consider clauses. And the good thing about superposition is that it's also, so we only have to consider superpositions that give smaller equations, in some sense of smaller equations. So we have to actually extend the ordering from terms to equations, but this is very easy. But the problem is that, of course, we don't know any such path between S and T. So we actually have to perform all superpositions between all equations to kind of cover all such paths. So the question is this really better than the initial naive approach? And well, my claim is that it's not really yet, because we just get from one search space explosion to the other, basically, because we still have to perform all the superpositions. But we get something very nice, which is this ordering, and this has some other uses, namely in redundancy detection that I will cover a bit later. And so now let's look at the order that we used in a bit more detail. So I have said that it will be called the simplification order. It's an order on terms that is, as I have said, well-funded. It's monotonic, and for the non-ground part, we also need this property, stability under substitutions, which means that if two terms are ordered in some way, then we can apply any substitution on these two terms, and the resulting terms will be also ordered in the same way. This is also a very natural property because we want to potentially instantiate equations, and ordered equations should stay ordered after instantiating them in any way too. And as I have said, we additionally require them to be ground total. And the two most prominent such orders in practice are the Knuth-Bendix order, or KBO, or the lexicographic path order, or LPO, that also Vampire uses. Yes, and I will come back to these a bit later. So let's look at now how the superposition rule looks like, actually. So this is the superposition rule, and I use this dotted equation to denote either a positive or a negative equation, so an equation or a disequation. And so the point is that we take some other equation, we find some subterm of the greater side of the right premise. So we have this condition here, which gives us that the left-hand side is the greater side. And we rewrite this such that because of this restriction, we get something smaller in the result. But this only covers the ground case. So when we move from the ground to the non-ground level, we actually have to perform unification. So we don't have yet that L is necessarily contained in the left-hand side of the right premise, but we have that there is some term K which unifies with L, and this unification gives us a unifier sigma, and basically we have to apply this unifier everywhere, so on the results, but also on the restrictions. And we also require that k is not a variable, because those superpositions are not needed for completeness. And we also have these strange looking new restrictions, but they are actually the same as these two. Just that when we move from the ground to the non-ground level, we don't have totality anymore. So the two terms may be incomparable, and we also have to take this incomparability into account. So we can only say that R sigma cannot be greater than or equal to L sigma, but they in principle can be incomparable, and this also applies to the other two terms. And when we move to full first order logic, then we also get some extra, so we get clauses that contain equations or disequations. These are the extra parts in the clauses in general, and these have to be propagated. And then there is also literal selection, and there can be other restrictions here and so on, but I don't want to go into detail here. There is a plethora of different superposition variants. Okay, and I have also said that I want to talk about saturation, so saturation-based reasoning. So in general, saturation-based reasoning is just a way to organize how we enumerate inferences, basically, given some inference system. And here's a simple saturation algorithm that suffices for our reasons. So we want to saturate a closed set S, and we do this as follows. We will maintain two closed sets P and A. P is the so-called passive set. These are clauses that do not yet participate in inferences. And the active set is, A is the active set, which contains clauses for which all inferences have been already computed. So we will maintain this invariant in this loop, that at the end of the loop, all inferences between all pairs of clauses in the active set A have been performed. So we do this loop as if the passive set is not yet empty, then we take some clause from it. We compute all inferences between this clause and all clauses in the active set. We get some clauses by doing this, and we look at these clauses, and if the empty clause is in the clause set, so we use this square notation for the empty clause, then we have established that the clause set is unsatisfiable, so we can return unset. And otherwise, we just put this clause C into the active set and put all the new clauses into the passive set. And when we finish executing this loop, and we haven't found the empty clause, and provided that our inference system is refutationally complete, then we can return satisfiable. Okay, so now we can introduce redundancy. So redundancy is this notion that not only ensures refutational completeness, but also is very important for efficiency. And roughly, a clause will be redundant in our notions when it follows from smaller clause instances in the search space. And the smaller here is the fixed simplification ordering, but we have to extend it from terms to literals and clauses. And this extension is, as I have said, it's very simple. We take literals as multisets of, so literals as equations or disequations, we take them as multisets of terms, and then we use a multiset extension to extend the ordering, and then we do this similarly for clauses. So we take a clause as a multiset of literals, and then we just use the literal extension of the ordering to and the multiset extension of this ordering to clauses to get the ordering on clauses. And so if a clause is redundant in a search space, then it can be removed without losing completeness. But of course, redundancy is undecidable because we have to check entailment in general. So we employ some kind of sufficient conditions to do this. And we use two kinds of redundancy elimination in practice that can be kind of categorized as follows. One of them is through a so-called simplifying inferences. So the idea is that when you have an inference like this, where you have some premises C1 to Cn minus 1 and D, and you perform this inference, and the C1 to Cn make the last premise D redundant, then you know that after performing this inference, or after adding Cn to the search space, D is redundant, so you can just, while doing the inference, you can just remove D. And one example for this is demodulation that we will also have a look at later. So demodulation works as follows. We take some unit clause with a positive equality, and if we find an instance of the left-hand side of this equality in some clause such that these conditions apply, then we can rewrite this instance into the corresponding instance to get a new clause, and then the right premise becomes redundant and we can remove it. Okay, and the other kind of redundancy elimination is so-called deleting, is through a so-called deleting inference. So here it's very similar to a simplifying inference, except we don't have a conclusion for this inference. So this is just kind of to organize our redundancy elimination into inferences. So we take some premises that make some other clause redundant, and then we can remove this clause. For example, subsumption is such a deleting inference. So when we know that there's when we find a clause C such that there is some other clause, and the part of this clause is an instance of C, and either there are extra literals in this other clause, or sigma is not a renaming, so the matching substitution that gives this part of the other clause, then C subsumes this other clause and we can remove it. Okay, and to introduce some simplifications into our saturation algorithm, we can do the following, which will be called forward simplification. So when after getting the conclusions of all inferences between C and A, you can just go over them and eagerly simplify or delete them with respect to the current active and passive set. And it is called forward simplification because we simplify or delete the freshly generated clauses with the old already retained clauses. Whereas the other variant is backward simplification, when we simplify the old clauses with the new clauses. And well, I don't want to go into any more details here. I think forward simplification is usually very useful. So we have some of them enabled by default in Vampire. Backward simplifications are maybe not as justifiable to be useful, but they are also useful in some cases. So let's just go with this algorithm where we only use forward simplifications for now. Okay, and this covers kind of the introductory part into saturation-based theorem proving and superposition reasoning. And now I want to cover one particular aspect of implementing forward demodulation, so the forward variant of demodulation, which is term ordering diagrams. This is a work that has been published last year in CADE, at CADE. So this is the demodulation rule again, and this is let's say a forward demodulation rule. So as I have said, there are these two restrictions. We have to make sure that the instance of the equation that we use is ordered this way, such that what we get in the conclusion is smaller. But we also have to make sure that the second condition holds, such that the instance of the equation is actually smaller than the clause that we are rewriting. But this second condition is not really important because it does not apply in many cases. The first condition is, however, very, very important. And so as I've said, it's a forward simplification because L equals R is in the active or the passive set and the other clause is new. And if you look at condition 1, it always holds if L is greater than R because of stability under substitutions. And for the same reason, if R is greater than or equal to L, then it never holds. So these two cases are easy to check because we can basically pre-process this when putting L equals R into the active or passive set. But there is the remaining case when L and R are incomparable. And in this case, we say that the equation is unordered, and we have to perform a so-called post-ordering check in this condition. It's a post-ordering check because we have to check the ordering condition after applying the substitution. And so for the two most prevalent simplification orders, KBO and APO, there are very efficient implementations. For KBO it's linear, for APO it's quadratic, and they are asymptotically optimal. But even though this is the case, post-ordering checks can be really problematic in terms of runtime. So here's a diagram where we show benchmarks from TP-TP, where with different configurations using KBO and APO we run problems, and we check each dot here is a benchmark, and the graph says the proportion of runtime spent with post-ordering check for each of these benchmarks. So as you can see, there are lots of benchmarks where actually the runtime is dominated by the post-ordering check, and this is only in forward demodulation. And there are even some extreme cases where we go almost to 100%. So what can we do to make these post-ordering checks more efficient? For these, we will introduce these term ordering diagrams. But to understand how we can improve things, let's look at how these post-ordering checks appear in saturation. So as I've said, we use some equations from the active or the passive set. So let's say we use this equation, and we have some new clauses that are always generated by doing more and more inferences. And when we want to perform a particular demodulation, let's say on T, we first have to match T with the left-hand side of an equation. And this, if it succeeds, then it gives us a substitution sigma, such that f of xy sigma is T. And then we have to perform this post-ordering check with sigma. But as saturation proceeds, we get different clauses, while this equation stays usually fixed. And we get different terms, different matchings. But the important part here is that even though we get different substitutions, most of these post-ordering checks stay very similar, at least. So this is one observation that we can make, that there are checks with the same equation and different substitutions. And there can be also equations in the active or the passive set, other equations, and in particular we are interested in the equations that have the same left-hand side. So for example, these two equations have the left-hand side f of xy. And for these we have this nice property that whatever term is matched with the first left-hand side, with the left-hand side of the first equation, it will be also matched with the left-hand side of the second equation with the same substitution. And this happens for all subsequent post-ordering checks too. So the second observation is that there are some checks with the same substitution but different equations. Okay, and so we have these two observations, and now we want to kind of use them, but to know how to use them, we have to look into the post-ordering checks even more. So let's say we now use a concrete simplification order KBO. And let's look at the operations that are performed during such a post-ordering check. So in KBO, it is a weight-based ordering. So we have to calculate some weights of terms and compare them. And then if there is a tie between the weights, then we have to do a lexicographic comparison. So we have to recursively also do some comparison between the arguments. And as I have said, for the same equation, we get different substitutions, but we get very similar post-ordering checks, modulo the substitution. And now what we can see is that, so if we start comparing the weights, for example, in this first operation, what we see, because the weight computation is based on just counting how many symbol occurrences are there and multiplying these by their weights and adding them up. It means that, for example, these two terms, no matter the substitution, these will contain two f's, these cancel out, and also some terms that are the same, because here is an x, here is also an x, here is a y, here is a y. So basically, regardless of the substitution, we know the result of this computation. This means that in all subsequent post-ordering checks, after we have realized this, we can just cancel this operation because we know the result. And if we go forward,
Martin, I have a question real quick.
Yeah.
Could you maybe you just need to repeat what you just said? Is this how do you know that these are always going to give the same result? Is this something particular to like the way that you're combining weights?
Yes. Yeah. So I try to quickly summarize how we compute the weights. So we literally just, so if you instantiate these two things, we just go over, so take all occurrences of each symbol inside the term, and all these symbols have a corresponding weight, which is given by some weight function in KBO, and we just multiply the number of occurrences with the weight, and then add these all up. And this means that whatever weights we have for x sigma will be the same also here. So this is kind of context independent. It doesn't matter where this x is, for example, because if we instantiate it and compute the weight, it will be the same.
Got it.
No places where we have an x. Okay. And okay, so sorry. Yeah, so I was saying that, so let's say we have already compared x and y in operation 2. And now when we look at operation 3, we see that we basically compared the same things again, namely x and y under the given substitution. And this has already been performed in operation 2, so we also know its results, so we don't have to perform this operation in all the subsequent post-ordering checks. And as before, when we look at this second equation, this will also have some corresponding post-ordering checks. And these are also very similar because of the structure of these equations. And we can do similar things. So for example, when we look at the weights of f of xy and f of xx under the given substitution, we see that there is an occurrence of f here and an occurrence of f here. These cancel out, and an occurrence of x here and an occurrence of x here. These also cancel out, so what remains is just an occurrence of y and an occurrence of x. And of course, these have to be taken with the given substitution. But we can simplify this weight comparison and have just y and x in all subsequent checks. Similarly, in operation 5, we compare the same term, so this will always give equal. And in this last operation, and let's say we have already compared or already performed operation 2 in the other post-ordering check, and now we know that the substitution is the same, so we know that in the given substitution we have already compared x and y. And this means that we can also skip operation 6. So as you can see, there are many things that we can skip, but how do we actually do this? And for this we invented these so-called term ordering diagrams or thoughts. And this is a term ordering diagram corresponding to the first post-ordering check with the first equation. And it can be evaluated as follows with the given substitution. So we have a substitution. We start here because this is the entry point with this incoming edge. We go to this node. This is a so-called term comparison node, and it just means that now we have to compare these two terms with the substitution applied on both of them. And if this comparison gives greater, then we have to take this branch and go to this next node, which is a so-called success node, which gives us this result that now we have succeeded in whatever we are doing. Currently it is a post-ordering check, and now we have a success with this equation, and now we can demodulate possibly with this equation. And if this comparison does not result in greater, then there are also some other branches which are usually not shown, and these all go to a sync node, which is also not shown. And the sync node is kind of the terminal node of the term ordering diagram. And maybe there is something strange here, is that we have greater equal, but we have this not greater than or equal to branch. This is just, so we could have 4 branches too, one for less, but we found that at least in the term comparisons that we make, it doesn't matter if we have less or incomparable separately. So we only have this branch. Okay, and so there are also transformations that can simplify these term ordering diagrams. And for example, for this term ordering diagram, we can get this term ordering diagram through the transformations, which is arguably a bit simpler. And these transformations are proven to be sound and terminating. So sound in the sense that they give equivalent term ordering diagrams in terms of term comparisons, and they are terminating, so we can reach kind of a normal form of a term ordering diagram if we apply them eagerly. And here's a quick look at the transformations. So we have some generic transformations. One of them is called redundant node removal. And this is used as follows. So if we have a node n1 and we go to some node n and then to an n2, and if we realize that we always move through this path, so when we go from n1 to n, then we always take this path and go to n2, then we don't have to go to n, and we can just replace this path with this path and go from n1 to n2 directly. And I will show you an example later. For this, there is node replication, which is just kind of needed for maintenance of the term ordering diagram and to make some reasoning simpler. And then there are the special transformations for KBO. These look kind of scary, but they just need to look scary to cover all cases. And then there is this third type of nodes where we actually do a weight comparison for KBO. And here are the transformations for RPO. These are somewhat similar to the KBO ones in the sense that they have to perform some kind of lexicographic comparison. But let's look at instead an example. And what I want to emphasize is that there are these transformations, but they are not really cheap. So we have to make sure that we don't apply them eagerly, because this is really a bad idea. And what we do actually is we evaluate the thoughts, and while evaluating them, we lazily transform the diagram as we go through them. And I will show you now an example of how this works with this term ordering diagram corresponding again to the first post-ordering check. And let's say we use a substitution where x sigma is equal to y sigma. So we start here, and I will show the current path through the diagram with this bold or like blue color. so we get to this node and we see that this is not transformed yet, and we can actually apply a KBO transformation. And if we apply this KBO transformation, then we get this new thermodynamic diagram with a weight comparison and two normal term comparisons that are for the lexicographic comparison. And now we are still at this initial node in the thermodynamic diagram, and we see that this weight comparison is trivial because 0 is always equal to 0. So we can use redundant node removal, and there is this branch which comes here, but we want to take this branch and go to the next node which points to the equal. So there is the equal branch coming out from this node, and we want to take this and move this branch to wherever the equal branch points. And if we do this, this node becomes unreachable, so we just delete it. So if we perform this operation, then we get this. So we have removed this trivial node, and now we have a simpler thermodynamic diagram with the new entry node. And now we cannot transform this current node because there is nothing to transform here. So we will evaluate it, and this evaluation, because of this constraint here, we will give equals. So we have to go through this branch, but we also marked this node as already transformed, such that we don't have to look at it again in terms of transformations. So if we do this, then we mark this as transformed with this red dashed pattern, and we go to the next node. And in this node, we realize that we have already compared x and y, namely in the previous. So on this branch, we have taken here equals, which means that on this branch, x and y are always equal. And using redundant node removal, then we can just take the equal branch from this node, which is actually not shown here, it goes to the sync node, and replace this branch with the two edges and this node in the middle with just directly going to the sync node. And if we do this, then we reach this sync node, and this gives the end of our evaluation, and we just exit. And we did not reach any success nodes, so in this context we cannot demodulate anything, but we got through this evaluation to this simpler thermodynamic diagram. And one very important feature of our thermodynamic diagrams is that they can support many kinds of term comparisons. In particular, we can, for example, put two post-ordering checks in sequence. So let's say we want to now insert this second equation into this thermodynamic diagram and the corresponding post-ordering check. So there is this other thermodynamic diagram which corresponds to the post-ordering check of this equation. And how we put them in sequence is as follows. We just take the sync node of the first thermodynamic diagram and simply replace it with the entry point of the second thermodynamic diagram. And if we do this, we get this new thermodynamic diagram. And let's quickly go through an evaluation of this, where we have now a substitution sigma where x sigma is greater than y sigma. Actually, sorry, I'm just looking at... okay, so how much time do I have?
You have about 10 minutes, but it'd be nice to leave some time for questions.
Okay, then I will, this is actually not so important. So we do a similar evaluation again, and we transform some things. So maybe I'll skip this part. And now we actually exit with, while also reaching this node. And this means that we can actually demodulate with this equation in the context of forward demodulation. Okay, and just a very quick example of how redundant node removal works. So let's say we have a thermodynamic diagram like this, and so we have already transformed these two nodes, and we are at this point. We also want to transform it. And we actually use a transitive closure over greater or equal and not greater than or equal to. And if so we run this transitive closure taking the information from these two branches, which is that gx is not greater than or equal to y and hy is equal to z. And there are also some additional axioms that we get from the simplification order itself. And now we can run the transitive closure, and we actually get that x is not greater than or equal to z. This means that at this point we will always go through this branch, no matter the substitution, and we can just replace these two edges with just one edge going to n3 directly. Okay, so we have an implementation of thoughts in forward demodulation in Vampire, and we did some experimentation. We used 3 modes: off uses no thoughts, on uses one thought for each equation, and there is a mode shared, which uses one thought for all equations with the same left-hand side, as we have seen in our example with the 2 equations. We used TP-TP benchmarks, in particular ones that had any post-ordering checks using some default configuration. And we used a roughly 60-second timeout, and both KBO and APO, but separately, and 2 different kinds of saturation algorithms. And here are the results, roughly. Well, what we concluded is that it's almost always better to use term ordering diagrams. So they are on by default, and the best configuration was this shared, where we gained lots of solved problems. And we also measured the proportion of instructions spent in the post-ordering checks, and this is what we got. And we had some look at especially at the unit equational fragments, where, as you can see, post-ordering checks are especially relevant. And we found that we got a speed up of, or at least a decrease of percentage of or proportion of instructions of at least 2 times, but in some cases up to almost 5 times. So this is really good, I think. So, for example, in APO, in the unit equational fragment, we went from doing post-ordering checks most of the time to doing them less than a quarter of the time. Okay, and we also looked at the memory, if thoughts use more memory or significantly more memory, and this turned out to be not the case. Yes, and to conclude, so I have introduced how superposition-based reasoning is used, and this is also used in Vampire. And redundancy elimination is key in Vampire success, and we looked at, in particular, forward demodulation and term ordering diagrams. And term ordering diagrams are really essential in the implementation of efficient reasoning with redundancy checking. And we use term ordering diagrams not just for demodulation, but also for example, ground joinability, which is a very expensive redundancy check, which is very useful, for example, in associative commutative theories. And we can also detect redundant inferences with them very efficiently, and there can be many other cases. We just have to implement these. And the nice thing is that with term ordering diagrams and some other optimizations in the modulation and some new strategizing, Vampire won the CASC's UEQ fragment for the first time in 2024. And last year it actually won all categories for the first time, including unit equality. So this is a big success, and here's a trophy. And the unit equality division from 2024. And thanks for the attention. I will stop here.
Thanks, Martin. We have some time for questions, and I figure I might as well leave the recording on. If anyone else would like to jump in before me, please go ahead. Otherwise, I will dive in.
Yes, please go ahead.
Okay. So I'll get started. So yeah, thanks a lot for this talk. I, you know, I think most of my questions are going to pertain to the first half, given my relatively low
Hmm.
knowledge of vampire. One of the things I found really surprising was this. I mean, the whole motivation for the work that you did on these Todds was that you spend so much time doing these ordering checks, and you know, I guess I found that very surprising, given that what my very limited knowledge of superposition is that you have to find all these instances of all of these potentially quantified equations over all these terms that are floating around, and the active set and passive set are growing, and you get learning this new clause all the time. You're constantly searching for instances,
Hmm.
and from what it sounds like, that's relatively cheap. Is that right?
Um, yes. So actually, if we can perform the modulations, then it's cheap. But if we cannot and we fail a lot, then it's going to cost us a lot. So in particular, in cases when we suffer a lot from these term ordering checks, is when we are looking at matches in maybe in the ballpark of like billions of matches and billions of these term ordering checks in like seconds, and these all fail, and we don't progress anywhere, and we are just wasting time trying to demodulate things. And there are some really really big terms sometimes that, I mean, yeah, usually terms explode, so you get some really big terms and big equations, and when you try to demodulate those, then it can take lots of time.
Right. Yeah, you showed some memory
And
usages that were in the hundreds of gigabytes, which that's an eyebrow
yeah.
raising number. Um, so the reason I asked about this, is the relative difficulty of that is part of me is, I don't know, thinking that, like, is there a way to combine the search? So in your phrasing, maybe I'm misunderstanding this. The post ordering check is like, oh, I have the substitution. And
Mhm.
now I'm trying to figure out whether the substitution behaves correctly with respect to the term
Mhm.
ordering. Um, but this sort of suggested, like, well, wouldn't it be great if I never generated this substitution
Mhm.
if if I knew it was going to violate the term ordering? And so,
Yeah.
is there an aspect of this to which you're doing? Is there some trivial checks that you could say, like, during matching, I know that I'm working on building up a substitution that is
Mhm.
going to be ill behaved, and so I'm just going to drop it on the floor. Do you do anything like that?
Yeah, to some degree, yes. Because, for example, in some strategies, we just drop all the incomparable equations. So we always have everything pre-ordered, and we don't try to demodulate with equations that have this property of the two sides being incomparable.
Mm.
But we also do some checks where, yeah, I mean, yeah, you can try to do some checks, and yeah, you can get some efficiency boost out of them, but um, these are usually not. I mean, you cannot either the check will be very sophisticated, right?
Mm.
Or if you want to do something cheap, then it's usually a very crude thing. But yeah, you're right that there is possibly something in between.
Interesting. Okay, thanks. Rudy, do you have a question?
Yes, I have a quite basic question. How does NumPy actually represent terms? What encoding do you choose to do that? And without, like, if you have two terms that are equal after renaming, I guess you probably store them once. And how is that happening?
Yes, so Vampire uses perfectly shared terms, and we just use these also inside the term ordering diagrams. So the diagrams themselves are just decks represented, however, in memory with pointers, and then we just use the shared terms inside also. So
Okay, does it need
we
some form of
yeah.
hash thingy of finding like hash consing, or what is perfectly shared mean?
Um, It means that when you first look at a particular term memory, and then you will represent the term by this pointer forever in the rest of the saturation.
Okay.
Everywhere. So so syntactic checks are syntactic equality is constant time like this.
Okay.
Yeah. We don't use any hashing, I think, because the opposite. So getting the terms is usually not needed from the map, because you always build them somehow from scratch.
Thanks.
Bill?
Yes, this is really interesting. I just may want to re-summarize what I understood what you were saying in different words and see if you disagree with what I say. So if you have a set of if you have a set of equations, but if you had a set of rules, you can combine work pattern matching all the left-hand sides into some kind of indexing data structure. So that's why it's too bad you couldn't talk about code trees. And this is sort of the analogous thing for sharing work over all of those ordering checks you might have to do in ordered rewriting. So that's, and then the term ordering diagram, is it kind of a BDD for a binary decision diagram, kind of for symbolically executing all those termination or those ordering checks?
Yes. So actually it's,
Okay.
It is some kind of very specialized BDD.
Okay.
Look at it like that.
That's cool. I've never seen something like that. That's cool.
Yeah, thanks.
I have one more question.
Okay.
So is this again sort of about the data structures as Rudu's asking you about? One thing that with the tools that we work on in this community, we're very interested in storing things up to equality, and we're really only working with ground terms. So I guess the first question is, do you store ground terms up to equality? Do you maintain distinct handles to ground terms that are equal? So maybe that's the first question.
No, but it would be really good to look into this actually. So Robin Cotelier also had his talk a few months ago, and since then we were actually talking about how we could use e-graphs or something similar in Vampire. This is not something we do, and some of our structures are really dumb. And
that's interesting.
So yes, it would be really nice too.
You're in a harder situation, of course, because you're representing a lot of non-ground terms. So I don't know how that complicates things, but I am guessing you're also storing a lot of huge ground terms. And so maybe there's something to take advantage of there.
Yeah, sure. So for example, there are some optimizations for ground terms in code trees. So when you have, when things become ground, then you can just use the pointers instead of the expensive matching and so on. So but on the flip side, there was also, I think, maybe last year, this talk about non-ground congruence closure, which might be also relevant in this context. I don't know if you know about this.
I saw a paper along these lines. I didn't read it.
And it was actually very complicated. So it turns out that when we want to apply similar things, I mean, I don't have a full understanding of how e-graphs work, but they are related to congruence closure, right? In some sense.
Definitely, yes.
Okay,
I'll check out this non-ground thing.
It looks like when you go from ground things to non-ground, the things become super complicated.
Right.
So it would be really great to look into these things.
Cool. All right. Well, we are at time. Thank you so much, Martin, for joining us. And I'm going to go ahead and stop the recording.